Welcome everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College London, and this is the new episode of the podcast Turbulence at the Exascale. So if you're not familiar with the podcast, we are trying to gather the view of the CFD and turbulence community regarding the challenges and opportunity associated with exascale computing. So this project is, this podcast, is part of the ExCALIBUR project, which is the UK initiative to tackle the transition to exascale computing with respect to software development. This is led by the Met Office, the UK Atomic Energy Authority, and the UK Research and Innovation. This podcast is, of course, also linked with the UK Turbulence Consortium. So today we have a guest from Spain, from the Barcelona Supercomputing Center. So my guest is Oriol Lehmkuhl, who is a group leader in the large-scale computing fluid dynamic groups in the Department of Computer Application in Science and Engineering. And as you can imagine, Oriol expertise is in CFD and high-performance computing. So good morning, Oriol.
Hello, good morning.
Thank you very much for talking to us today. So I'm going to start with this question. And for those who don't know you, please, can you tell us a little bit more about yourself, where you are from, what you have studied, and how did you end up at the Barcelona Supercomputing Center?
Yeah, I'm from Barcelona. I studied mechanical engineering in Terrassa. That is one of the, in Barcelona, there are two main engineering faculties. One is in Barcelona, the other is in Terrassa. Terrassa is about 20 kilometers from Barcelona. And when I was at my grade, one of the professors that we have here in the Mechanical School of Terrassa, he was beginning to do HPC. So he was beginning to, he was building the clusters by himself. So putting standard desktops together and putting, using network, the typical network of internet to connect everything. And he was beginning to build DNS codes, no? To run very simplified heat conduction, natural convection problems. And that was my beginning. I was at the grade beginning to interact with this guy. And at one moment, I liked this more than the actual mechanical engineering lectures. And from that, I began after my master to do the PhD there. And we did begin, instead of using like more structure meshes, to begin to build an instructor code. And my expertise, if you look all my CVs, to very complex geometries. So that was because on the PhD we were building this instructor code, and we did a startup all together with this research group, and we were to try to do consultancy with HPC. That was impossible in Spain. We did have good times, and this company was working. I was working there. They still work there, 10 years. But after I see that if I wanted to go bigger and to follow my passion, that it's to try to push the CFD as much as possible, I needed to move to another place, and BSC was perfect, no, for that, because they are always pushing the new technology. So that was the reason I moved to BSC, and the reason I have been working this like 5 years there. Yeah.
5 years, great. And what do you like about working at BSC? What's the great
I
things
like
about
that. Yeah, so it's the main concept, no, that the director has, that it's not just to build a big machine and just the operation department that is helping the users to the machine. If not, it is to have as well research areas on all the different applications and hardware directions that you could have, no? And to have this all together, so experts on the different applications that are pushing for their own, book, it's very interesting, no? And then because in my department, I can talk with people that they are interested on biomechanics, or they are interested on sociology, and they are pushing HPC on that area. And this is a very enriching, interaction for me.
Excellent. So can you briefly describe your current research activities? Just what are you doing these days?
Yeah, in general, we are focusing a lot on aeronautic applications, introducing scale resolving methodologies into their design pipelines, and as well on automotive and energy. Okay, these are the main activities where we have a lot of competitive projects and we are working with companies. And it's always the same, trying to introduce scale resolving and time resolving methodologies in their lives. Okay.
Excellent. And in the Department of Computer Applications in Science and Engineering, just how many people are working there?
We are around 90.
90.
Yeah, 90 researchers, almost 100. Yeah, and with different lines. So there is combustion, there is pure CFD, there is biomechanics, but there is people working on tsunamis, on geographic more problems, and even on social sciences. Yeah.
Excellent. And final question, sorry, I'm very curious. Do you take PhD students or master students? Yes. Okay.
Yeah, we have PhD students, usually linked by some of our research projects. And we have master students. We take internships. Usually they come from UPC. Yeah.
Yeah.
And they can stay with us like 6 months, participating on some of the research we do. Yeah.
Great. Excellent. Right. Let's ask you now more specific question. I know there is in terms of CFD in Barcelona, there is a big work around ALIA, the code. And so can you tell us a little bit more about this code, and in particular, what's the strategy to use CPUs and GPUs for ALIA?
Yeah. So ALIA, it's a code that was initially developed by Guillermo Zhu and Mariano Vázquez, no? That they are one of the group leaders there at CASE, and he has been growing a lot. We have around 30, 40 researchers working there. And first was just fluid mechanics. Now there is solid mechanics, there is electromagnetics, particle mechanics, radiation, etc. No, there is a lot of different physics altogether. I think one of the main strengths of ALIA is the possibility of doing multi-physics and coupling problems at very large scale. It's one of our passions, one of the things that all the main developers we like a lot, and we think that it's one of the futures, no, of computational mechanics in general. So we are pushing this quite a bit. And of course, we are now on this problem that all the different groups have, that how to transition, no, how to use these heterogeneous machines with accelerators, etc. So at the moment, we are working quite a bit on that. For the physics that is more simple for us, that is fluid mechanics, we have extensions to GPUs using OpenACC mainly. And we have my colleagues, especially, this is especially the group of Guillermo Zhu, they have been working a lot trying to get good performance. It's hard because we use linear finite elements mainly. So the computational arithmetic is not very high. And we work very well on CPUs. But when you go to GPUs, you know, you have more difficulties there in order to get all the use, no, that they could have. No? But they are working on dynamic load balancing strategies in order to have several instances, some instance of ALIA working on the CPUs, other instance of ALIA working on the GPUs, and then looking the correct balance. And when you do that, then we choose more or less okay, no, the GPU doing these strategies. We have some papers on that working with airplanes, no, and doing like looking how we could benefit of those machines.
Great. And
then we are as well trying to research other type of numerics, no, instead of using linear finite elements, to use high order finite elements. And we see that then you use well then the GPU, but the benefits that you get when you do scale resolving are not that big at the moment. So it's something we are researching in general.
And is it written in Fortran or in C or?
It's written in Fortran. Yeah.
In Fortran.
And then we use Python a lot for the post-processing. We have a lot of extensions to Python.
So the strategy on GPUs is to combine this Fortran base code with OpenACC. And I guess on CPUs, it's MPI, or you're doing MPI,
It's MPI.
MPI.
It's MPI.
Okay, great. Thank you very much. And I guess the code is open source. So
it's available source, but you need to do some paperwork to get it because we are a national center. So you could have the source if you need it, or you can just ask for binary files if you don't care and you want to have it installed on a particular machine.
Thank you very much. I've also noticed that you have been doing some work on wall-resolved and wall-modeled LES of active flow control for external aerodynamics with Alaya and also with Charles. So can you tell us a little bit more about this work around large simulation?
This is something we have been pushing even when I was at UPC. I was doing some research studies at Stanford at the group of Parvis Moin, and we were beginning to look to use wall models on very complex geometries and relevant Reynolds number for the aeronautical industry. This has been growing. We have done a lot of cross-validation between the code of CTR, the Charles LES, of Cascade actually, and our code. And it's very interesting because they use finite volumes, we use finite elements. So we can showcase that there is a methodology that if you do low dissipation schemes with traditional physical basic models and you use certain wall models, independent of the type of numerics that you use, if you do your homework correctly, then you can reach very similar results. This is important to make sure that the industry wants to use, because the industry is more interested in the methodology, not on specific codes. And we have been doing all this work. Also, now we are working on the high lift prediction workshop and comparing our results with other codes from the States, also with very good comparisons when you have the correct meshes, and in order to understand which type of mesh you need to go to these large scale problems. And of course, to understand limitations. We know that with wall models, we are predicting very well high lift aircrafts, but we know that we have problems in laminar to turbulent transitions. We want to identify these limit conditions in order to have good practice guidelines for the people that is going to use wall model LES on those scenarios. And then with Adrián Lozano Duran, that it's one of was postdoc at CTR and now it's professor at the MIT, we have been playing with the second derivative. You say, okay, now we can do these simulations of aircraft with LES thanks to wall models, but let's see if we can do some physics, and we can try to get some recommendations on the physical point of view, already. And we were playing with that, on this summer program that Javier Jimenez has, and we were trying to look if it was possible to use active flow control in order to alleviate the stall conditions of high lift devices. We were playing with that, and we have been we have selected some parameters that we think that they could work well, and they can help to mitigate the stall at very high angles of attack. Okay.
Excellent. And may I ask you what type of active control solutions you are looking at?
We were looking at zero mass flow type of active flow control. Yeah.
Great. Thank you very much. I've also noticed there is another research area where you are fairly active. It's related to particle deposition in the respiratory system, and in particular, it's very important for drug delivery. So can you tell us a little bit more about this this research?
This is a research we do in collaboration, of course, with the Guillermo Zhu group, that they have been doing this on BSC a lot of years. And I have been helping them to improve on the turbulence modeling, to improve as well on the understanding of the flow, that because it's very complex. And actually, I can say that you don't have as many shortcuts that we have on when you simulate an aircraft or when you simulate a car. What you can, we can have some shortcuts on the modeling because we can use world models, because the Reynolds is very high, and then the subgrid scale models, they work very well. But inside of the respiratory system, you are at a transitional flow. So you go from laminar to turbulent to turbulent to laminar. So the best model almost is to do almost DNS. So for the wall interaction is very complex because in reality it's moving. You have the mucus, so you cannot really use wall model. You need to resolve the boundary conditions or the boundary layer, and at the end you use very fine meshes. And HPC is very important if you want to do it correctly, no? And if you want to really try to solve this problem of how the drop is interacting with the wall, and if the drop is going to stick or not, no? It's going to go to the final part of your airflow, no? And it's a very interesting topic of research that we have a lot of things to do because we still are not coupling with the movement of the respiratory system. Now we have some first words while we are trying to couple with everything, no? With the pulmon, etc. And there is as well the interaction with the thermal part, no? The moisture that you have, how this interact with the drug. So there is a lot of work to do there. And it's a poor multi-physics problem. That's the reason we like a lot, no? And there is work as well to do on the post-processing. So now we were using for first time dynamic mode decomposition in order to understand how the big scales of the air are interacting with the drug deposition. So I think there is a lot of advanced techniques that now have been using, people is using on channel flows, on more simplified problems, that it's important that we do the exercise to go through to understand better the physics inside our respiratory system. Yeah.
Thank you. And you are using Alaya for this?
Alia, yeah. We use Alia, and then it's not just Navier-Stokes. We couple with a Lagrangian solver to have the particles as well, etc. Yeah.
Great. Thank you very much. Right. So now I have a few questions about exascale computing. So I guess most of your research is based on Alaya, and based on your experience and your expertise, what do you think are the main challenges if in the future we want to perform high fidelity or turbulence resolving simulations on exascale or on pre-exascale computers? I mean, it's already ready for CPU and GPU architectures, but do you see any challenges in the future? Like if you increase the number of cores, is it going to scale, or is it load balancing issues? What do you think?
There are several problems, right? And the first one is post-processing.
Okay.
So I think that post-processing, we are not ready for that in general. We have some big tier 0 praise projects where we are, because we want to post-process more things, no? There is a concept I like a lot from Professor Jimenez, no? That he's pushing a lot to me, no? The best thing that he has done a lot of things, but the ones that I like more is to begin to think, to say, okay, we cannot just look the flow like the experimentalist, no? That usually we do the same, no? We put the sensors very similar the way the experimentalists they do, and that's it. But here we have so much more data that we can apply more rich techniques, but those techniques, they need to store a lot, almost all the data. You do almost like a scale resolving databases. And then this is a lot of space, and it's a big challenge if we increase the size of our simulations after to do the post-processing and to understand all the data that we are generating. So there is a first challenge, that it's how we are, if we are improving on this enough, no? And if we really are ready to have petabytes of data that we need to access, and we need to get the information, because if not, we are wasting the resources, no?
Of course.
If not, at the end, if we do just a very big simulation, but we just get the same know-how that the experimentalists they can have, okay, it's true that maybe for designing, we are lowering some costs, no? Because, you know, we have, maybe we have something that it's not as expensive as the experiment, maybe because things are getting, we are using a lot of energy, really. But we need to get more, no? We need to get more insight that after it's going to have something that it's going to be first complementary to the experiments, but at one day it's going to surpass the experiments. And to that, then we need to tackle the challenge of how to generate a lot of data and how to understand this data, how to get reduced information from this data that it has physical meaning. And for that, I think we are not ready. At least I'm not ready, and I do very big simulations. And it's a big problem that we will have, I think. And for the parallelism, it's true. I think that for some cases, we are reaching the strong speed up limit, no? So if we are already doing a scale resolving of aircraft, and we are not mesh converging, but if you give me a machine that it's 10 times bigger, I could mesh converge that. And then the problem is that maybe I'm still too slow. Maybe to do that simulation if they give me 1 million cores, I can go 2 billion, 3 billion, even 10 billion cells, and be at the limit of the model. That in this case is the wall model, no, the limited, because there is one moment that you cannot refine more the wall model, because you are going to begin to compete with you are going to begin to have structures on the boundary layer that compete with the wall model itself. So there is one limitation of the cell size that you have, that this is the limit, and you cannot not improve. You need to change a modeling approach if you want to improve. So imagine that you are there and you have 1 million cores, that this is pre-exascale, no? It's not really the exascale. You do that simulation, you are at your strong scalability limit already. But maybe you need 1 week to do the simulation because we need to solve the time, no? And at the end, the time steps are very small, and we need several flow-throughs. Maybe you did 40 flow-throughs around your main wing, no? To get the statistic converged. So the question is, if I'm already at the strong scalability limit because my space, maybe I have 10,000 cells, and you cannot go beyond that, okay? So what we can do, no? And I think that for some applications, we are beginning to reach this limit. And then this is a problem because industry maybe wants this results in 8 hours and not in 1 week, no? But you say, I cannot go further because of the time statistics I need to do. So I think it's going to be important to begin to think on kind of paring time algorithms, no? Where you can do farming of your time statistics, no? So because, and then we need to begin ways to reach the steady state, the statistical steady state in different ways, no? And then you can do in parallel and accelerate. So this is something that we are not doing yet, and I think it's important to use the exascale machines, because if not, for some applications, we will be already at the limit of our spatial scalability, and it will be not possible then to go and say, okay, I want to do a very long time integration of that. No, we cannot accelerate that. So we need to think on this type of techniques, maybe. Yeah, great. This is something, because I think for the other things, I'm sure that it's going to be managed. Low balancing, you know, there is a lot of experience of that. People is working a lot, at least on BSC. I know a lot of my colleagues on ALIA, they're working on load balancing, integration with GPU and CPU, and it's going to be managed, okay? So I think other problems like the data, like how we can accelerate the time statistical averaging, etc. These are things that we need to build new algorithms if we want to go to exascale.
Great, thank you. And based on your experience at BSC and well, you can see your other colleagues in other field of research, do you think that the community or in Barcelona, people are ready for the transition to exascale, or do you say, well, in CFD we are more advanced, or what's your feeling about that?
My feeling is that people is still not ready to the final step of the pre-exascale. So there is not that many people, really using the several petaflops consistently and generating the data that requires, etc. So this is going to be a big change that requires as well change on the code factoring, etc. And I think people is still not ready. And there is one part of at least in Barcelona, one part of the research community that maybe they don't need that yet. So they have a lot to do with the current machines and the pre-exascale machines that are going to be on an hybrid space. So I think it's something that it's pushed by the top end research, because of course there is money to go there, but the main community of CFD, for instance, is not going to take advantage of that on the next 5 years, I think, in my opinion.
Okay, and I have a question in terms of hardware. So you have been using CPUs and GPUs over the years. I was wondering if there is one thing that you could change about high performance computing, and I'm mainly thinking about hardware. What would you change?
To me, the memory clock, yeah.
Yeah, no, I'm saying, for example, yeah, if your code is memory bound, then you will want to have more memories or more network, more, or different architectures. I don't know.
Yeah, in general, ALIA has evolved very well, and now we have discovered in our latest analysis that we are not that memory bound. That this was a traditional problem for CFD, and we have improved a lot on that with vectorization, dynamic load balancing, etc. But anyway, my feeling always is that if you give me more memory, if you give me faster memory, this is like a huge improvement always for us, And it's not like that much the CPU clock and things like that, that we can adapt doing more parallelization. And yeah, the network, it's true that we scale well for hundreds of thousands, but if you go beyond, yes, the network always it's a problem, no? Yeah, but the memory, I think, could have a better impact on our daily basis simulations.
Yeah. Thank you. I have two more questions for you. One is a very well, there are two hypothetical questions. If I give you access to a big exascale computers tomorrow, what will be your first simulation on?
I think it will be on wind energy. Yeah.
Wind energy.
Yeah, because on wind energy now we have begun to couple mesoscale and microscale models. So we can do LES of a wind farm maybe of 20 kilometers by 20 kilometers, resolution 1 meter. But when we couple with the mesoscale, we can do 2 or 3 days, no? And then you see the evolution. But if you give me an exascale machine now, I can do a simulation of 1 year, because you farm each of those days with the conditions of the mesoscale, and it will be a very nice application. And then we can have on certain wind farms that we know are very hard to predict, and some of the companies we work, they have very big troubles to understand what happens. We could have a very insightful, simulations I think in a time that now it's impossible. Now you say, no, I need a year to get your J, so we cannot do it.
Yeah. Great. Thank you. And I have one last question. We are talking a lot about exascale computing and getting ready to this. But my question is, what do you think will come after the exascale era? And do you think we're going to see a continuation of what we have now? So GPUs with more memory, more energy efficient, more power? Or do you think we are going to have a big revolution in terms of hardware, and we will have to rethink and redesign all our software? What do you think will happen in like 20, 30 years?
Hard to tell, yes. I'm sure that there will be this line of being more and more energy efficient, because we need to be aware that we are using a lot of energy for our simulations. It has a huge impact on the planet at the end. No? So I remember at the beginning of my PhD, usually the numerics guys we were saying, no, it's the guys of the wind tunnels. I remember I was at NASA EMS and they have those big wind tunnels that they need a power plant just for that, etc. And now it's the other way around. No, we are the ones using as much energy, so we need to be very aware of that. And the only way to have more computational power is to improve that. But it's true that maybe there is a paradigm shift. That's true. I'm not sure which one it's going to be, and I'm not sure if we are going to have time ourselves in our career, no, to do these big changes, no. But in general, I think that most of the activity is going to be to have more and more energy efficiency, and to be critical on that, no. The cost of the computation, if it's worth it, if you take account the energy that you are wasting on that.
Great. Well, thank you very much, Oriol, for your time and for your inputs on this topic of CFD and high performance computing. We wish you all the best for your future endeavors, for your work with Alaya and so on and so on. Thank you everyone for listening to this podcast. As usual, you will find the link on our Twitter account, UK Turbulence in one word, or you can also Google the UK Turbulence Consortium website. Is just UK Turbulence in one word, and you will find all the links for this podcast. So thank you, Oriol, again for your time.
Thank you. Yeah.
And thank you, everyone, and hopefully see you very soon for